just how, I don't know, precise it all is. How does a photon know exactly which electron to interact with and with exactly the right energy every single time? It feels almost, yeah, impossibly precise.
It's a really deep question. And our deep dive today, drawing heavily from the cosmic dance of light and matter, actually offers a really compelling way to understand this fundamental relationship. We're hoping to sort of demystify that precision for you.
Absolutely. That's the mission here, really, to unpack the core ideas, the rules governing this intricate link between light and matter. We want to uncover the surprising facts that show how these incredibly precise interactions actually make perfect sense. Think of it as a shortcut to grasping one of the bedrock principles in physics. Okay, so let's unpack this apparent precision. Because you're right, at first glance, this perfect match between a photon's energy and where an electron can go, it does feel almost supernatural, like there's some secret code involved.
Yeah, it does seem that way. But what's truly fascinating, and maybe a little less mystical, is that the principle underneath it all is just a beautiful example of the conservation of energy. A photon's energy isn't just randomly precise, you see. It's often the direct result of an identical but opposite energy change that happens somewhere else.
Ah, okay.
That's the real heart of why and how these energies are so connected.
So it's less about cosmic magic and maybe more like cosmic bookkeeping, universal accounting.
Right.
To really get this, we probably need to picture the electron's world inside an atom. They're stuck in these specific quantized energy levels. We often draw them as orbitals.
Right.
And the key thing is they absolutely cannot exist in between those levels. It's like an elevator that only stops on floor 3 or floor 5, never floor 4.2.
Exactly. That's a great analogy. And that restriction defines the whole energy transaction. So for an electron to jump up to a higher energy orbital, it must absorb the exact energy difference. No more, no less.
The precise fare for that elevator ride.
Precisely.
Yeah.
And conversely, when an electron falls back down from a higher level to a lower one, it spits out, it releases that exact energy difference. And how does it release it? As a photon. It's a perfect exchange every single time.
So you mentioned the analogy. Think of it like a perfectly sized key for a very specific lock. The photon's energy is the key. And the energy gap between the electron's orbitals, that's the lock. And this is where it gets really interesting, I think.
It does, because this whole dance is dictated by one of the most fundamental laws we know.
Yeah.
The law of conservation of energy, the universe's ultimate bookkeeper, as you put it. Energy isn't created, it isn't destroyed, it just gets moved around or transformed.
Yeah.
And this law absolutely governs how photons and electrons interact.
Right. And our source material lays out basically 3 main ways this happens. First, scenario A, the perfect match. This leads to absorption. This happens if and only if the photon's energy is precisely the same as the energy gap between the electron's current spot and a higher available spot. If it matches, boom, the electron absorbs the photon, jumps up, it gets excited.
And it's not just theoretical.
No, not at all. This is actually the principle behind things like atomic absorption spectroscopy. It's how scientists can figure out what distant stars are made of or identify materials just by seeing which specific colors, which wavelengths of light get absorbed.
They're looking for those missing keys.
Exactly. Then scenario B, the mismatch, no absorption here. If the photon's energy is just wrong, either too high or too low to match any available jump for that electron.
Then what?
It just sails on through. The photon either passes straight through the atom or maybe gets scattered, bounced off in a different direction. We see this happening all the time. Rayleigh scattering, for example, that's what makes our sky look blue. Blue light photons get scattered more easily by air molecules than red light.
Right, so the air molecules aren't absorbing them, just redirecting them.
Precisely. And finally, scenario C, overwhelming energy. This leads to ionization. This happens if a photon comes in with so much energy that it's actually greater than the energy binding the electron to the atom in the first place.
So more than just the energy for a jump.
Way more. Enough to just knock the electron clean out of the atom, ionization. And any leftover energy from that photon, it doesn't just vanish.
Conservation of energy again.
Exactly. It gets converted straight into the kinetic energy of that electron flying off. Every last bit is accounted for.
And this incredible precision, this energy matching, it's all wrapped up in quantum mechanics. There's a fundamental equation, AE, HEF, that connects the energy difference between orbitals directly to the photon's frequency, F.
H being Planck's constant.
Right, the constant that links them.
Yeah.
It basically says a specific energy gap always corresponds to a photon of a specific frequency, a specific color, if you like. It's just baked into the rules of the universe.
Okay, that paints a really clear picture of how these photons and electrons interact. But it does raise a question, doesn't it? Are all photons created this way? Are they all perfectly sized for these electron transitions? Or are there other processes out there making photons that are, well, improperly sized for this particular job?
Great question. And the answer is a definite, resounding yes. The universe is absolutely full of photons created by processes that have, well, nothing directly to do with electrons hopping between orbitals and atoms.
Like what?
Well, for starters, think about nuclear transitions. Inside the nucleus of an atom, the protons and neutrons also have their own quantized energy levels, much, much higher energy levels.
Okay.
When transitions happen there, they release incredibly high energy photons. We call them gamma rays. These pack such a punch, they're generally way too energetic for a simple electron orbiter jump.
So a completely different scale of energy.
Entirely different scale. Then you have something even more exotic. Particle-antiparticle annihilation. When a particle meets its antiparticle, like an electron meeting a positron, poof, they annihilate each other.
Obliterate each other.
Completely. Their entire mass gets converted directly into energy, according to E.C. Kachat. And that energy comes out usually as 2 or more very high energy photons. Again, not typically the right energy for an electron jump.
Wow. Okay, what else?
Another one is synchrotron radiation. This happens when you take charged particles, usually electrons, get them moving incredibly fast near the speed of light, and then use strong magnetic fields to force them to curve, to change direction.
Like in a particle accelerator.
Exactly like that. Or in space, around things like pulsars or quasars with intense magnetic fields. When these fast electrons are forced to turn, they radiate away energy as a broad spectrum of light, including things like X-rays. A whole spread of energies, most not matching atomic transitions.
Okay, so that's 3 sources of mismatched photons.
And here's a fourth one that's much more down to earth. Thermal radiation, or sometimes called black body radiation. Basically, any object that has a temperature above absolute zero. So pretty much everything emits light.
Just because it's warm.
Yeah, fundamentally. It's due to the random jiggling and vibrating of its atoms and molecules because of their heat energy. This random motion shakes loose photons across a whole continuous spectrum, a wide range of energies. Think of the glow from an old-fashioned incandescent light bulb filament.
Right, the warm glow.
That glow is thermal radiation. It's a chaotic mix of photons with all sorts of energies. So yes, even everyday light sources are producing tons of photons that atoms will simply ignore. It's like this constant silent chatter of energy happening all around us.
So the universe really is swimming in these improperly sized photons that weren't made by an electron dropping down an energy level.
Absolutely. But here's the elegant part. This doesn't cause some kind of cosmic traffic jam or problem. Atoms are incredibly selective. They simply ignore these photons if the energy isn't right, if the key doesn't fit the lock.
The door doesn't open. It's like having that huge collection of keys you mentioned earlier, millions of keys of all shapes and sizes, but only the one that perfectly fits the specific lock will actually turn it.
Exactly. The atom acts like a very precise filter.
So it's not just about the energy existing, it's about the receptiveness based on quantum rules.
Precisely. That's the core argument, really. This seemingly magical, perfect match between photon energy and electron transitions isn't magic at all. It's a direct and beautiful consequence of 2 things. Energy being quantized, coming in specific packets, and the law of conservation of energy.
And those photons that do fit.
Often those photons that are the perfect match are like energetic ghosts or echoes of past electron transitions somewhere else in the universe. They carry that exact quantum of energy needed to trigger the very same transition in another atom. It's this incredibly selective nature of quantum mechanics that ensures electrons only pay attention to photons carrying the correct energetic key.
What an incredibly elegant system. It really takes you from feeling like there's this impossible precision, this magic,
to seeing this deeply logical, almost inevitable outcome of fundamental physics. Governed by conservation of energy, by quantum mechanics, there really is a profound beauty in that precision once you see the rules.
Absolutely. And if you connect this to the bigger picture, I mean, think about it, this fundamental grasp of how light and matter talk to each other. It underpins so much of what we do in science and technology.
How so?
Well, everything from understanding the composition of stars billions of light years away just by analyzing their light,
Right, the absorption
to
rate.
designing new materials right here on Earth with specific optical properties, like for solar cells or lasers. It all comes back to controlling or interpreting this fundamental photon-electron interaction.
It really is foundational. So maybe a final thought for everyone listening. Consider how this incredible selectivity, this pickiness of atoms, shapes not just what we can see and measure.
But also everything we can't see. All those improperly sized keys constantly flying around, what insights might we gain if we start looking not just for the keys that fit the locks we know, but maybe start trying to understand the significance of all those other keys, the ones that don't seem to fit?
That's a fascinating angle.
Keep exploring that cosmic dance happening all around you, even in the parts that seem silent or invisible.